ever wonder how pilots do this? For those people who don't know what this is, it's called a loop-the-loop. This is performed during an air show of a pilot, and a lot of people ask, how do they not fall down? How do they keep still in their seats even though they are oriented upside down? Well, this is because of the two forces acting on it, the gravitational force and the centripetal force. The centripetal force acts as a outward force that pushes the pilot on the center of the loop, and the gravitational force pulls them. So even though the pilots are upside down, the combination of gravity pulling them down and the centripetal force keeps them comfortable in their seats throughout the loop. So hello again everyone. For today, we are going to be talking about another topic, which is Johannes Kepler's three law of planetary motion. But before we start, I have read something online and I want to share it with you all. This law were based on Nicholas Copernicus's theory and Tycho Brahe's observation. I don't know if I pronounce it right, but it's Tycho Brahe. So Tycho had taken very accurate observations of the planet, and he found out that Copernicus's theory was not quite right, which is the heliocentric theory, and he was not quite right in explaining the planet's motion. But unfortunately, Tycho died in 1601, so Kepler inherited his observations. And several years later, he made his three laws. But he only did the first two laws in 1609, and it took him almost, I don't know, at least a decade, less than a decade, to finally finish it with the third law. So yeah. Before we get into the three laws, what does the law of planetary motion tells us? Well, it describes, of course, the motion of the planets in our solar system and how it revolves around the sun and such. So yeah, that's what we're going to talk about. Let's start with the first law of planetary motion, which is the law of ellipse, where this law states that the planet revolves around the sun in elliptical orbit as the sun as its focus. Let's draw an ellipse, and then let's say this is our planet. And this is our sun, which is always the focus. Every time the planet moves, as it revolves around the sun is always its focus. So that's how the law of ellipse works. And let's proceed with the second law, the law of areas. It states that the radius drawn from the sun to the planet sweeps out equal areas. Let's draw an ellipse again. And let's say our planet is here in point 1 and it travels here in point 2. So this is its area. Let's call it as area 5. And then our planet decided to go to the opposite direction. It travels from here, point 6 to point 7. And this is its area 8. So area 8 and area 5 is equal because that's what the law of areas states, that the radius drawn from the sun to the planet sweeps out equal areas. That's basically it. So let's proceed with the last and the third law, which is the law of orbits. It states that in an elliptical orbit, an elliptical orbit is directly proportional to the cube of its semi-major axis. And to make it simple, it basically says how long a planet takes to finish one revolution. The longer the distance, the longer the time it takes for the planet to travel. So that's it. I hope you learned something on Kepler's 3 laws of planetary motion. See you on the next video. So hello again everyone. For today we are going to talk about the law of universal gravitation by our very own Isaac Newton. So before we start, I have a little story, of course, like always. And Newton first discovered the gravity when he was sitting by an apple tree on late summer in 1666. And he first thought of the system of gravitation when he was hit upon by an apple that fell from the tree. And because of this apple, he began observing it, how it falls down the tree, and he figured that there is something that is pulling the apple out from the tree. And that's when he discovered the law of universal gravitation. And this is the universal gravitational equation. F is equals to G multiplied by the quantity of m1 multiplied by m2 over r squared. F is the gravitational forces between the two bodies, and m1 and m2 are the masses of the bodies, and r is the distance between the centers of two bodies, and g of course is the universal gravitational constant. It is always equal to 6.673 times 10 raised to negative 11 nm squared over kilograms squared. My good example for this would be my classmate friend is very concerned about his weight, but he doesn't do anything about it. And after we learn about Newton's law of universal gravitation in physics class, he becomes concerned about all the possible effects of a change in Earth's mass upon his weight. And during a rare free moment at our lunch table, he speaks up. How would my weight change if the mass of the Earth increased by 10%? I answered Fred, and I told him that even though there is a 10% increase in the Earth's mass, which was extremely unlikely, it wouldn't have that much of effect on his weight. It would have an effect, but it is not noticeable because gravity is what determines our weight. Actually, from an equation, our weight is equals to F grav multiplied by our mass, which means that if we want to decrease our weight, maybe I told him that maybe he can travel to Mars, I suppose. Because the gravity is different there, and his weight would be slightly more different than it is here on Earth. So that's how the law of universal gravitation works. And I hope everyone learned something, and I'll see you in my next video. Bye. So hello again everyone. For today I will share with you all another experience that will help you gain knowledge about centrifugal force again. So, here goes. During our summer break, I had a part-time job on a local amusement park nearby, and I got a chance to guide children, and it was very very fun. And there's this one time that all the kids were so curious about the rides in the park, especially the spinning teacups. Oh my god. So they were so curious, and one kid asked me what was the magic behind it, and one kid shouts out,
"How is that possible?"
and so since the kids were so curious about it, I began explaining it to them. But of course, since they are little kids, I explained it to them in a fun and engaging way. So I told them that there are special forces that are working together throughout the entire ride. Kind of like the Avengers, the famous superheroes that are very, a lot of kids know it. And yeah, the first force that I told them about was the centripetal force. And it pulls us towards the center of the circle. So as the ride spins, the floor pushes back our feet, and it keeps us still in our seats. And the faster we spin, the stronger the push of this force is. That's why whenever we feel a little heavier when the ride accelerates or speed up, it's just the centripetal force doing its job. So, yeah. And when we stop, that's when another force comes in. It's called inertia. Inertia is like the tendency of an object to keep doing what it's doing. So when the ride slows down, our body wants to keep spinning in a straight line. That's why we feel a little bit dizzy, a little bit woozy when we get off the ride. So, yeah. So I told them that it's all about forces pushing and pulling us throughout the ride. And I told them that physics is all around us, especially in fun places like the amusement park. And by understanding these things, I hope that the children were enlightened by it, and you as well who is watching this video. So I hope you learned something, and yeah, that's all for today. Thank you so much for watching these videos, and bye.